programs and general manager and director of precision machining operations. Mike began his career in engineering and worked in design, manufacturing, and systems engineering. Mike has been awarded with 2 US patents in his career. He holds a Bachelor of Science degree in mechanical engineering from the University of New Haven and was elected to both the university's athletic and engineering halls of fame. He was awarded an honorary doctorate of engineering from the University of New Haven in 2019. Mike also earned a Master of Science in Systems Engineering and Engineering Management from the Massachusetts Institute of Technology. Additionally, Mike serves as on the RBC Bearings Board of Directors. Mike also serves on the University of New Haven Board of Governors from 2015 to present, and is currently the Vice Chair of the university's board. I'd like to introduce up now Mike Ambrose.
Thanks. Hi, everyone. So I'm very honored to be here today. I'm a big fan of CCAT and all that they do for the state of Connecticut. What I'm going to do is I'm going to give you a perspective on artificial intelligence and machine learning, and I'll talk more about that from an OEM and also from an end customer perspective. So what that means largely is Department of Defense. And I know not all of you might be involved with Department of Defense, but it is a good, I mean, there's where a lot of the investments are, and you'll get insight into really where all this technology is taking you. So thank you, Nasir. That was a great setup because there's some definitions in there that are going to be really important. So what I'm going to do is I'm going to start real simple. I'm going to start with the product value stream that all of you should be familiar with, but in the context of what it means from a digital integration standpoint and ultimately artificial intelligence. So if you look at this chart, I mean, this should be all familiar. You start with, you're going after a business, you take it through design, you take it through manufacturing, build, assembly, you have a supply chain in there, ultimately you need to test it, validate it, certify it, and then you need to support it in the field. If you look at that, really what the whole digital integration is, this whole industry 4.0 is, the theory is you have a single source of data that is continuous throughout that whole value stream. Really simple concept. And for the most part, where we are, and Sikorsky, not unlike a lot of other OEMs, really got good and focused on the design integration and the manufacturer integration, how you use this data, how you use computer-aided design, computer-aided manufacturing is where it started, to be able to get better efficiencies, lower cost, better performance. What really where this is today is how you extend beyond that to all aspects of that product value stream. Again, sounds kind of simple, but in reality, it's really complicated because what you end up seeing is that in order to really fully define a product, and especially a product as complicated as a helicopter, but even if you had a toaster, you're probably still talking tens of thousands of interfaces required to fully understand what that product represents digitally and how all that single source of data can be used throughout that product value stream. So in the case of a helicopter, and this was, you heard Nasir, my last 18 months at Sikorsky, I was going to retire. They said, hey, can you go figure this out for Sikorsky and Lockheed? And the first thing I saw is, wow, really complex. And anyone who thinks it's not complex, we'll talk afterwards. But really what you're looking at here is you're looking at every single step of the way, every single component, and there's tens of thousands of components in a helicopter, needs to be understood on what data is important and how it interfaces with all the stakeholders and all the interfaces along every single one of these steps. And oh, by the way, you have a customer on the bottom, because if you go back to the previous chart, typically, historically, the way it worked is the customer would interface at specific points along the way. They would have requirements. They would have preliminary design reviews. They have critical design reviews. They would have test reviews. Then ultimately, they're responsible for the validation certification, in our case, airworthiness. Discrete data points along the way. Well, the way it's going to be in the future, and it will be this way, and for the supply chain, this is a paradigm shift, is that relationship, that data is going to happen concurrently along the way. that also applies to the supply base. So it's very important to understand as I go through the next 15, 20 minutes on how your role is along all these steps, because basically supply chain, you get requirements historically, you go and build something, you design something, you build it, and then you get it tested to criteria, very discrete points. That's not the way it's going to be in the future. And it's already changing. And OEMs are trying to figure out, and I will say this a couple of times from my presentation, we don't really know the answer in terms of what's important and what data is required. And really neither do our customers, but we need an engaged supply chain to figure it out. So let's go into it. So what is this digital integration, and what does a single source of the truth really mean? What does it enable? I'm going to start with a couple of terms that you've probably heard. I'm going to just put a little context into how it really matters and why it matters to supply chain. The two terms are model-based system engineering and digital twin. Now, whether you're experts in model-based system engineering or not, it is the way we're going to do business going forward. And basically, if you think about like doors, or if you think about, you got an RFP, or you got requirements in the past, model-based system engineering is the means for the entire digital product value stream to be connected. It's through that interface, understanding all of those interfaces with all the computing power that goes with it and required to be able to understand how those requirements get linked to those millions and hundreds of thousands of interfaces. So it's a very critical concept to understand, and understand your role and how you're going to interface with model-based system engineering. Digital twins, essentially that's a digital representation of a physical product, system, process that really ends up being indistinguishable between that physical product, system, and process. Why this is so important is that for this to work, it has to be connected throughout this whole value stream. So you're going to hear terms in the future, if you haven't already, about things called physics-based modeling, where data is pulled in your case, if you're the supply chain, you're going to provide data that helps an OEM, helps a customer like the DoD be able to digitally represent what your product can do in a larger system. So what that allows for like Sikorsky, and Sikorsky has done very well on things like X before UX. Now, maybe some of you might have heard what that means. I'll explain a little bit more. I mean, X before UX is like build before you build, design before you design, test before you test, fly before you fly, maintain before you maintain. In order to do any of those, you have to understand, have the right data, and be able to simulate either physically, in the case of like a virtual 3D system, on how you can interface if you want to maintain and see if there's a better way to go and like maintain a system, or the way we've been able to effectively use it at Sikorsky is that we can go through hundreds of iterations of designs, and then also have manufacturing engineers look at, as we iterate like a blade design, there's a lot that goes into a blade. Dynamic stability. We need to make sure it's got the right stiffness. We have to make sure it has the right performance. It has to be producible. It has to be, environmentally strong. There's so many variables that go into it. Historically, it would take us like 6 months to like almost a year to design a new blade, just design it without even really going beyond that. We're now using things like this X before UX, iterative simulation, optimization, and even pulling in machine learning. We've taken that from like 6 to 8 months down to like about 4 weeks, because we're able to do it concurrently. And that's a major, major incentive for these integrated digital concept is that everything becomes concurrent. And you need a lot of data to go do that. So let's go dig into what that means. From a high level, the end objective from this single source of data is to have a digitally integrated product value stream. You've heard me say that a couple of times, so that you can have digital twins. And there's many manifestations of this digital twin. Ultimately there's a overarching digital twin, but there's a manufacturing, there's a supplier digital twin where you have your actuator or you have your your subsystem. But then there's also like a flight test digital twin that we use in our industry, which is really how it performs. And then there's the most important one from a customer standpoint is this sustainment digital twin that I'll use as an example. So when you have this integrated digital twin, the common sense thing is, yep, you can go faster. You should be able to save a lot of money because you have less iterations. You have a product that's better quality and a product that's better supported. So how does artificial intelligence come into this? And you see, Nasir did a good job on the definitions. One of the subsets of artificial intelligence is machine learning, and it's probably the most important one for the supply base to understand, because machine learning is where you're able to go use all that historical data, allow the algorithms and the data analytics to go and learn from that historical data to make predictions about either optimization, prescriptive analytics, or predictive analytics, where you're able to go and see how systems perform based on that historical data. So really important to understand the role of artificial intelligence, machine learning in this whole construct of digital integration. So let's go into artificial intelligence and machine learning use cases. So helicopter, it could be anything up here, really. In the digital integrated world, like I said, toaster ovens become really complicated because you have to understand all of those interfaces. But typically the way this works, and Nasir talked about, when you're looking at something like predictive analytics, predictive maintenance, it starts with sensors. Now, if you're in a factory, if you're making parts, you need to have the right kind of sensors to understand how your systems, how your machines are performing. That's all information, that's all data that you can then use to be able to apply things like machine learning. Understanding the right strategy on how to do that is critically important, and you'll see that in an upcoming chart. But you can see, if you break it down, predictive maintenance, prescriptive analysis, I said that's where you use data to try to optimize solutions, optimize designs. Emerging, there's been a lot more predictive analytics. Predictive maintenance has been around for about 15 years now. It continues to evolve as better machine learning tools develop. But something to keep in mind is that it isn't only about the product itself. There's a lot of cost benefits once you understand or able to connect to the digital twin to be able to make predictions around things like inventory optimization when you understand predictive maintenance, predictive analytics. So when you're hooked in to an OEM, a customer digital twin, that's now information that can see, like, how do those products perform? So in addition to understanding machines and how machines perform, is that you start to use this stuff for other parts of that value stream where cost and inventory management and optimization become very important. Another one that I want you to be aware of, and how customers are using this information, and it's also from a strategy standpoint, is that not all parts need to be the same in the future. Yes, you're going to design parts that have a certain number of life to meet a certain performance requirements. But in the case of like the DoD, in the future, you're in a battle. You've got an asset out in the field, helicopter, tank, whatever. You need to keep that asset in the fight. So what will happen in the future is, based on how those parts are used in applications, you might not need to have a 10,000-hour life. You might only need to have a 200-hour life to be able to get to the next phase inspection. So what will happen in the case of like additive manufacturing with customers is that they're going to need the information that you provide, and they're going to look at how that particular vehicle could have been damaged or needs maintenance, and they'll tailor a part to be able to go and get them to that next phase and be able to do it in a matter of days or hours, versus taking that helicopter, tank, whatever system out of the field and maybe be down for weeks, months, so forth. Important concept as a supply chain, because one, you're going to be required to facilitate that. Two, you need to understand what that means for your overall strategy, so that is there a role for you in supporting customers to make that happen. Things like training simulations are obvious. Generative AI is another thing. The chat GPT, we're starting to use that a lot for, research information. How are other people doing things? So I won't get into that. That's pretty obvious. Okay. This is the money chart for the supply chain. So really what I want to talk about, and I'm not going to have answers, I have opinions and perspectives on each one of these, but these are the questions that each supplier needs to understand and needs to have a strategy and a plan around. It begins with, so what is your value proposition? Because it's going to change. The way you made money, the way you had value in the past is going to be different in the future. It's already happening today. And so when I talk about things like additive manufacturing, you heard me talk about how customers want to use this information, for the benefit of warfighters or the benefit of the end customers. You're going to need to understand exactly what your role is and how you go do designs, because designs are going to happen a lot faster. Iteration, evolution is going to happen much, much faster than it already has. And it's happening already. The next thing is, so what data is the right data? You heard me talk about millions of interfaces. What we're seeing, we were seeing at Sikorsky, and what you see at most big companies is this is a lot of information. It's expensive. And not only information is required. When we do a flight, we will generate terabytes of data on one flight. Now, do we need terabytes of data? No. Well, that's where machine learning comes in, because it's able to go and analyze that data. So we get down to the specific information that's required to go and understand what the next flight needs to do. You're going to find the same thing the more you get into AI, the more you get into digital integration, is that your customers are going to be requiring you to provide a lot of data. Be honest, we don't always know what the right data is. That's why it's important for you to get smart on this, because you'll be able to go work with customers, say, no, you don't need terabytes of data. You only need this interface, because these are the key features required to really understand how this product's going to perform. Formatting and managing data interfaces. You're going to need to know how to, it could be different, but everybody has different systems. They're always going to be evolving. You're going to need to know what is the right type of data for, what's the right type of formatting for that data interface. Customers are going to ask you for certain formats. You might not need to provide it if there's a way that it could be translated and it's useful for the suppliers. Storing data, big companies can make large investments. Supercomputers cost about $10 million each. Most suppliers aren't going to be able to afford supercomputers to go process data. So you'll need to understand what your strategies around that. Cybersecurity goes without saying is that, what does it mean? Because again, OEMs might not, and customers are going to ask for, the highest levels of certification. You'll need to have a strategy on that to make sure you're compliant, one, but also make sure that it's in a way that provides value for your end customers and also protects you and your IP. So IP strategy is something that I think everybody's struggling with. You're going to need to spend a lot of time on that because it is evolving. And I will say is that, information is what is required here. That information is your IP. And so we could probably spend 3 hours just talking about what is an IP strategy. If you're not thinking about it already, you better be thinking about it. So the last two charts are just really, for the people who are already doing this in terms of automation. I'm not going to go into exactly, what the benefits are. Nasir actually did a nice job of articulating some of those. What I want to just emphasize here is that from an OEM, from an end customer standpoint, this information that you're using to be able to go have better quality parts, to be able to go reduce cost, is information that will be requested and may be required from your end customers. So you do need to go back to that IP strategy, understand, one is how is that useful for them? How does that become something that is a competitive discriminator? And I just want to close one thing on this chart is that if you aren't doing this, you need to be doing it. You better be doing it because your competitors are going to be doing it. And like you heard me say, is that in many cases, your end customers are going to be doing it. It may be one of those strategies as well. Like if you look at something like, additive design, generative design, additive manufacturing, there's possibilities and probabilities that one of the objectives is that parts could be designed out of systems, parts could be integrated. Anyone who's spent more than half an hour, and if you haven't had a chance to really walk around what's happened here at CCAT, take a look at what they're doing from an additive manufacturing standpoint, additive design standpoint, because it is here. You do have novel concepts where you can have better performance, lower cost, cheaper parts, better sustainable parts. And part of that is that how does that design evolve in ways that we would have never been able to imagine even 5, 10 years ago? And so when that happens, there's a possibility that the products that you provide either can go away, be done by some other function, some other part, or will be done in a way that is totally different the way you've been doing it for the last 10, 15, 20, 50 years. So you do need to understand where that goes. You also need to understand your role in physics-based modeling. So a term I referenced up front, because the data, that information is what's required to do digital twins, to do these simulations for larger systems for overall products. So important concept. And then just the last is really, if you're not doing this already, is we found literally like 50-60% reductions in time to go and get products designed and built by having this integrated optimization. And ultimately, we've seen quality improve by like 90% on average. So when you do this, it absolutely works. So with that, I hope you get a lot out of it today. I hope this is a good opener for all of you. Thank you so much.
Thank you, Mike. Yeah, at this time, we'd like to invite the audience to ask any questions that you have up until this point.
Yes. So there's a lot of, good question, because the government will ask the same thing. What you're seeing is the transition. So you saw like that first chart I had, we're not on the second chart yet. We're still like doing things like, very prescriptive in terms of reviews and design handoffs. There are aspects, because I've been asked this by 4-star generals many, many times, because I've been able to point to, this is where it's applied and this is where the benefits are. Especially when it talks about like designing a blade. That's a concrete example of how we were able to go take it from 6 months down to 4 weeks. We could prove we showed it and we built it that way. But what ends up happening is that there's still a lot of parts of the digital thread that aren't there yet. And I use the example of, we did a great job. And I've seen this, it just isn't my example. I've seen other examples where you can go and implement like digital thread and say, look, we took it from, a year down to a week. And, but what we didn't do is we didn't realize that like the tool required to go like and assemble that part was out of a catalog that somebody just didn't realize the standard lead time, because they were designing the old way, was a year. And that would have been fine in the old days, but the entire digital thread wasn't connected. So you still have aspects that are not, and companies are still doing it the old way. So the more you get connected, and this is why there's such a drive to get the whole thing connected, that's when you'll start to see the savings. The other thing that needs to change is that there's a procurement process, there's an acceptance process. All of that needs to evolve also. And that won't evolve until you have more of the thread connected. So that's why. And you're being kind in terms of how long it takes to get something certain. You're being like really kind, because there's and you're not really, for all those reasons, is that until you get more of it connected, you're not going to see the benefits. But it doesn't mean that you should, it's a journey. And what you see is that when you get that little piece connected, you see the savings there. And it's like you've got to just have a holistic approach. I think it's a little bit easier for suppliers, but for the OEMs, you can imagine the DoD, you can imagine the complexity. Yeah, it's funny. First question I get asked by 4 stars. Yes.
What experience have you had, or is Sikorsky looking at where reinforced learning and data that's actually generated from other data, especially to balance good versus bad data, like failures versus success?
Yeah. So, that's a really good question also, because there has to also be a validation, trust but verify. And so if you look at example like flight, again, this is not just us, this is anyone who's been involved with this, is that you need to have a trust but verify. And so, if you're dealing with something like flight safety, you just don't trust the data. There has to be a validation of the data based on actual tests. And then the way like predictive maintenance works is that when you show that cause and effect and be able to use things like machine learning to go help you look at scenarios. So a great example is if you look at like you're testing a tire envelope. So imagine you have a big envelope, corner of the envelope. What you end up doing is you get test data, actual test data on like corners of the envelope. And then using machine learning, artificial intelligence, you're able to run the simulation, say, well, if this point is true, then the risk that this is going to be, or the probability this is going to be true is much greater because there's less variability, less risk. So that's the approach that industry is taking and the customer is taking, is that you validate some of the test points, and by validation, you're able to make decisions around points in between. Does that make sense? Strategy, though, so there has to be a planning that goes into that. That's why people still matter. Still that engineering degree is still going to matter. Yeah. Yeah. Still for a long time. Yeah. Okay. Now I could be around to answer questions after. So thank you.